Hello, everyone. I'm Carola Bibiane Schöndeb. I'm a professor of applied math at Cambridge, and I will give you a status update now from the AIX COVNET team on ideas and preliminary results on our work on AI-assisted multi-stream data integration to improve diagnosis and prognostication in COVID-19. The objective of our work is to create an open source software tool to support COVID-19 patient management in hospitals. Our tool will be designed as to take multi-stream data as an input, including chest imaging data, X-rays and CT, clinical and laboratory data, which is then fed forward to an AI toolbox or an algorithm toolbox that consists of mathematical statistical techniques as well as AI type deep learning, machine learning approaches, which are processing and analyzing this data and then turning this data into appropriate predictions relevant for different diagnostic and prognostic clinical phenotypes. These phenotypes are then used in turn for patient triaging, treatment planning, and hospital resource management. In this talk, I will mainly touch upon the imaging-related challenges that are involved in this endeavor and present some preliminary results and open challenges. Our team consists of clinicians, biomedical researchers, mathematicians, engineers, and computer scientists working on the clinical questions and clinical phenotyping, on the definition of, in particular, the clinical questions and the clinical phenotypes, on the data collection, the data curation, as well as the data processing analysis, and of course, the algorithm development. The team members come from the UK, in particular Cambridge and Imperial, from Austria, from Vienna, and from Germany, from Munich, as well as from China, from Macau, with partnering hospitals and partnering companies from around the globe. So please look at our website for a comprehensive list of team members. The website will be displayed at the very end of this recording. Our strength in the team that we have gathered is really the close dialogue that we have between clinicians and data scientists, and really the passion that we all bring for advancing AI solutions for COVID-19. For developing meaningful and impactful algorithmic tools for clinical support, we need to make sure from the very beginning that we are targeting the right clinical questions. In our team discussions and after a thorough review of the existing recent literature, both on the clinical as well as the AI side, we identified the following unanswered clinical questions, which we believe are crucially important for effective patient triaging and treatment of COVID-19. Here, I emphasize a few. Which patients need to be admitted to the hospital, and at what point during the course of the disease? Which patients need to be admitted for oxygen therapy in a general ward versus a high dependency unit? Which patients will deteriorate and need admission to intensive care for invasive ventilation? Can we predict which patients will progress into a bacterial pneumonia and when? So we can adapt treatment accordingly. Can imaging predict which patients will develop a heart versus lung phenotype? And can we predict which patients will get pulmonary embolism or microthrombotic complications? And last but not least, can we use X-rays, chest X-rays, to monitor the disease and its treatment? Exemplarily picking up the last point, here a visual documentation of really the subtlety of COVID-19 biomarkers of severity in simple chest X-rays. The changes from very subtle line patterns to consolidation and GGOs are very hard to quantify by eye. Hence, severity quantification based on CXRs, as one example, clearly is an area where AI can help. After defining the important clinical questions, our starting point for the algorithm development was, of course, in the review of the existing recent literature. First, what are the existing AI imaging tools available for COVID-19? Here, a very incomplete list of a couple of broadly speaking AI solutions that have been coming out from both universities and AI, biomed, tech companies. What these tools can do is already very impressive given the short time we had to react to the pandemic and the usually small data these algorithms have been trained and tested on. However, despite these early successes, there still remain several gaps and open challenges in the algorithm development which need to be overcome before our clinical questions from before can be answered with the help of AI. Again, emphasizing a few of them. The first one is data scarcity, small data sets. There are few public data sets available. Almost all the data are from only a few sources, mainly China. So data might not represent the global population. Also, something to keep in mind is that COVID and non-COVID examples might not necessarily be comparable. Also, recent papers, like the one of O et al., find no statistically significant differences between COVID-19 and other viral pneumonia X-rays. So the question arises, what are the boundaries of model performance? Most work has been performed for diagnosis. What factors are important for prognostication and severity prediction? And the last point, almost all existing work focuses on the lung tissues. However, the heart potentially is also a very important organ for prognosis of COVID-19. In this context, let me highlight some specific image-related open problems we need to address as a community. The first one is that the main focus so far has been on high modality data, such as CT, which is natural due to the outbreak happening in China, where CT is predominantly used. This is in strong contrast to a lot of other countries, for instance, most countries in Europe, where X-rays are predominantly used for screening and treatment monitoring. There is, with imaging, of course, again, very, very present this small data challenge. We need to develop models which can work in the small data regime. Some keywords here being semi-supervised learning, transfer learning, or patch-based approaches, as for instance in the work of O et al. Multimodality and longitudinal data analysis is another crucial point to consider. How do we combine different imaging data, clinical and laboratory data, and how to use this in predictions over time? In particular, in the case when measurements have not been taken in equidistant time intervals. Models need to be developed, last but not least, with clinical guidance. It's crucially important that data analysis, algorithm developers like us are developing these algorithms in correspondence with clinicians. We need to focus on what is actually useful in the clinic. Turning from these general considerations to the work of the AIX COVNET team that I want to report about, let me go with you briefly through some preliminary results we achieved in the last about 6 weeks since we started our work on the 23rd of March. In particular, I will give an overview of the overall framework we have in mind for our multi-stream analysis, and then highlight 4 individual components of it. Namely, the standardization of the imaging data, exemplarily shown for CXR, lung pattern segmentation from CTs, the general problem of varying data input and how to handle missing data with data imputation techniques. And the fourth one is this interplay between lung and heart features, lung and heart phenotypical expressions, conditions, by looking at the segmentation of calcifications from CT images for studying the interplay of COVID-19 with heart conditions. So starting with the overall framework, Our multi-stream analysis roughly consists of 2 stages: a feature extraction stage and a classification stage. The first one is about data pre-processing and feature extraction. For the imaging data, which could be X-rays, CTs, or both, we are investigating some standard feature extraction networks at the moment. Then we also need to think about feature extraction for more complex clinical laboratory data, for which we are investigating both classical feature extraction methods, such as PCA, as well as more bespoke feature extraction strategies. This step also includes, of course, data cleaning, standardization, data imputation, etc., that I will allude on actually in the next slide. In the second stage, we want to classify. We want to use these features that we have extracted from the data to classify into the different clinical phenotypes that are interesting or that are important, crucial for the patient handling. So here we want to integrate the multi-stream data, imaging and non-imaging data. And we are currently pursuing, considering 2 options. One is a fully supervised approach, and the other one is a semi-supervised approach. While we are currently exploring both, our main emphasis will be on the semi-supervised framework, in particular graph-based methods, because those are likely to be more robust to small amounts of labeled data. They are amenable to handle missing data problems as well. So the data imputation could almost be integrated into the classification step. And potentially they also allow for the discovery of new classes. So now highlighting a few things that we have looked at so far. So one of the subtasks that we have been looking at is CXR pre-processing, in particular standardization and enhancement. As the way to the creation of sufficiently large data sets for training and the way to derive classification algorithms which are generalizable between data coming from different hospital sites, actually this step of standardization is really a crucial one. In particular, let me highlight that non-standardized measurement procedures are potential confounders. Confounders, in particular, thinking about later biases that they might create in any type of classification, any type of data analysis that comes later if not taken into account. They are likely a major source also of overstated performances in some publications, as networks do not pick up clinical phenotypes, but differences in the X-ray or CT scanner measurement and image reconstruction processes. So far, we have investigated the standardization and enhancement for X-rays, in particular developing a solution that combines segmentation, cropping, adaptive histogram equalization for the standardization part, and different filtering techniques, for instance, maximum or median filtering for the enhancement of the images afterwards to be more prone for robust classification. The second example I want to present is about lung pattern segmentation from CT scans. Here, I'm showing the results achieved by our team members in Vienna, who have been developing a lung and lung pattern segmentation tool that we are currently fine-tuning for COVID-19. The approach is a UNet-based approach that works in 2 steps. One is the segmentation of the whole lung. The other one is the classification of the lung into lung patterns like GGOs and consolidations. In the figure on the right, we show a comparison between 2 results of the Viennese automated lung pattern segmentation approach, comparing the automated output when trained on one data set versus when trained on another one. So the first one is trained on this MedSeg dataset. The second one is trained on the LTRC dataset, and then applied to the dataset that we are currently curating in the AIX COV team. Apart from the fact that the two have slightly different classes, what one can also see is that the attention of the classifier is in roughly the same regions, with the MedSec maybe being a bit more conservative. Of course, the results are very early days and need a lot more fine-tuning, but even in its current form, one could really already imagine that feature extraction like this one could make up a really valuable input for further phenotype classification. So data variability, I said before, is another issue that we are looking at quite closely in the AIX COV NET team. In particular, we are thinking about how to deal with gaps in the data, varying availability of input variables, when working with such a multi-stream analysis tool. We are exploring here, roughly speaking, two strategies for addressing this. One is data imputation, so imputing the data before doing a further classification. And the other one is the development of classifiers that are robust with respect to missing data, that can handle missing data. For the first approach, we are currently evaluating a relatively new deep learning based approach called GAIN with well-established imputation techniques such as MIS-Forest and MICE. Our preliminary results performed on a toy dataset of endometrial cancer patients suggest that MIS-Forest gives the most reliable imputation, but that GAIN has potential for being further developed to become more robust with a potentially higher gain in terms of accuracy. For the second strategy, we only have very preliminary results yet, looking at a toy dataset called IRIS. Compare the table here on the slide. Without telling you much more about the technique that we call robust forest, and which is developed by our team, let me say it is indeed holding up to comparison with approaches from the literature so far. So the last point is about this link between heart and lung. So while COVID primarily affects the lungs, the heart can be involved, and pre-existing cardiovascular disease is a marker of an adverse prognosis. Patients with COVID-19 are at risk of complications, including other lung and heart diseases such as pulmonary embolism, pneumonia, and heart attack. In collaboration with researchers in Utrecht and Harvard, we are developing CNN-based detection and segmentation algorithms to segment out coronary artery calcification and cardiac chamber and pulmonary vascular volumes on CT scans. Here I show an example of the development of an asymptomatic coronary atherosclerosis during and after COVID-19 infection, visualized by a series of CTs. In the top row, what we can see is the overall chest imaging, which in the second and the third row, we are zooming in, we show local views of a coronary atherosclerotic plaque showing the change of calcified tissues. The fourth row shows the lung damage induced by COVID-19 infection. We want to quantify the appearance of such calcifications with automated calcification segmentation methods. Preliminary results achieved by our collaborators in Utrecht seem promising for automatically segmenting calcifications. Here, a two-step CNN approach has been applied. This algorithm allows us to determine the calcium burden on different parts of the heart. In the left image, we show the calcium identified in the thoracic aorta for a COVID-19 positive patient from China. And on the right, we show the calcium identified in the left anterior descending artery. This calcium burden will be used for prognostication of patient outcome. So what I showed are all quite preliminary results of a very active collaboration that is working on several bits and pieces towards our AIX COV NET multi-stream analysis vision. Some immediate next steps from here are linking the analysis pieces for CXR and clinical data for COVID-19 severity prediction and prognosis, a fine-grained analysis of clinical phenotypes on the basis of CT, developing an analysis pipeline that is robust towards varying input and output requests, so working more on the data imputation side of things, investigating semi-supervised training approaches. Again, we made a lot of good experience with those in previous works that we did. So this is certainly a component in our project that is quite dominant. And robustification, and something that I haven't touched upon yet, uncertainty quantification for developed algorithms and associated predictions. With this, I want to close just reminding everyone again of our overall goal to develop an open source tool for AI-assisted diagnosis and prognostication in COVID-19 and its rapid clinical translation. So please do get in touch if you want to collaborate. Here a link to our website and our email address. We really think that this rapid development that we need to do now really can be achieved as a community by working very closely together with clinicians, with regulatory approval officials, with software developers, and with, of course, mathematicians, engineers, and so on, like myself, who are very keen on making our expertise available for this cause. Thank you very much.